Welcome along, ladies and gentlemen, to your weekly SETI Talks series. Today we're very lucky to have a SETI PI join us today, and that's Laurie Fenton. She's going to talk to us about sand seas in the solar system. Say that 5 times fast. I hope she will.
No, I won't.
Laurie did her BS in astronomy at UMD, and where she was working with John Pearl on opacity measurements of the Martian atmosphere using Mariner 9 measurements. And then she did a PhD at Caltech on Martian aeolian systems and their interaction with the atmosphere and the Martian atmosphere with Arden Elby. And then she did a postdoc at ASU before coming to NASA Ames and the SETI Institute in 2006. She is extensively published in, particularly in Mars and aeolian processes, and so she is the expert to talk to us about dunes and alien processes on Mars. So if you'll join me in welcoming Laurie.
Thank you. Can everyone hear me? So I'm going to cover 3 broad topics. The first topic is an overview of sand seas, what are dunes, what is sand, so that you have a general idea of what I'm going to be talking about, and maybe hopefully so that after today, I don't know, if you're walking on a beach or you're flying over the Mojave or maybe Utah and you look out the window and you see dunes, or you happen to be walking and you're walking on sand, you have maybe a better understanding and hopefully a better appreciation for what it is that you're seeing. Then I'm going to move on and talk about generally what we see in terms of sand and dunes and sand seas in the solar system. And then at the end, I'll talk about some work I've been doing that hopefully contributes a little bit to our understanding of sand seas on Mars. So first, I knew I wouldn't be able to avoid using the term aeolian, and I wanted to be very clear what I meant. I'm not using the word alien. Aeolian has a separate little syllable in it. It's got an extra letter in it or 2, and what it means is the work of the wind on a planetary body's surface. I'm not talking about little green men. It's something that in planetary science can be easily confused, particularly here at the SETI Institute, so I just want to be clear. The word comes from Aeolus, who was the keeper of the winds in Greek mythology. Some think he might have been a god, some think he might have been immortal, but that's generally what he was known as. And so Aeolian means the work of the wind. There are 4 aeolian worlds in our solar system: Venus, Earth, Mars, and Titan. I had to be careful. I can't call them planets because Titan is not a planet, it's a moon of Saturn. What they all have in common is observable surfaces. So for example, Jupiter and Saturn might have aeolian surfaces, but we don't know because we can't see down that far. And they all have sustained atmospheres. So for example, Mercury and the moon have very tenuous atmospheres, but they can't really hold on to them. So they can't really produce aeolian features on the surface. But I'm going to move away from the solar system for a little while and talk about the Earth to give you some context. So first of all, what is a sand sea? When I say that, what am I talking about? Well, that really depends on who you ask. So I'm using the definition that comes out of one particular textbook. These guys say that a sand sea, which is sometimes also called an erg, is an area spanned greater than 30,000 square kilometers that is covered by wind, at least largely by wind-blown sand, some of which may have accumulated into sand dunes. A dune field is the same thing, but smaller than a sand sea. Here's a really nice example of a sand sea in southwest Libya, right smack in the center of northern Africa, and it's a really, really nice example of that. Here's the sand. It's basically a great big basin that's been filled up with sand. And what's nice about it is that you can see this river of sand coming from upwind that's pouring sand into this basin. You can almost think of this as a stream pouring into a lake, where it's filling up with water, or in this case, sand. And there are some mountains on the downwind side that are trapping that sand in that basin, although you can see some outlets of sand pouring out the other side. So okay, that's a sand sea, and you could have seen that maybe there were some sand dunes in it. What's a sand dune? Well, here's a really nice example of a simple sand dune. This is from last year's trip to the Kelso Dune Field, which is in the middle of the Mojave, and I highly recommend that if you ever get a chance, if you're ever driving through the Mojave, go to it. There are paved roads all the way there. It's a beautiful, beautiful sight. I went there last year with a couple of my summer students, and you can see the head of one of them disappearing off into the distance here. These are big sand hills. These are big dunes too, off in the distance, but what I wanted to show you was this nice simple dune in the foreground here. What you see are three different components. The windward side is called the stoss. It's usually covered in ripples, and basically what's happening is sand has been blown from the left to the right to produce this dune. And it crosses over the brink and avalanches on a slip face when the slip face oversteepens. Here's another example. This is from White Sands National Monument in New Mexico. Again, a beautiful, beautiful place to go. The sand here is made out of gypsum. That's why it's white. It's a pretty rare thing to see on the Earth. Usually gypsum gets dissolved and reprecipitated and it forms rocks or it just disappears. In this particular location, it can form into sand, and that sand piles up into these gorgeous, bright white sand dunes that look like snow. And here's a person off in the middle distance for scale. So when I took this picture, I was standing on what is effectively the stoss of a dune, and you can see what was once a brink and a slip face here, but it's been eroded away and rounded off a little bit. Off in the distance, though, you can see a very nice sharp brink and a slip face. So there's another nice example of what a dune looks like. So let's go even more simple. What is sand? Those of you who are geologists probably know this already, but sand is not a composition. It's a size range of particles. So things greater than the size of sand are gravel, things smaller than it are silt. And the size range of sand is defined to be between about 2 millimeters down to 62.5 microns. And so for those of you who aren't used to thinking in terms of microns, 100 microns is about 1/10 of a millimeter, so a little bit smaller than 1/10 of a millimeter, up to about 2 millimeters. Also, notice these colors, yellow for sand and green for silt, because they show up in the plot on the next slide. Here we have sand-sized grains, and here we have silt. This is a plot of particle size versus the strength of the wind that's required to move sand particles. So if you're ever standing on a beach or on a dune and you scoop up some sand in your hand and you look at it, you realize that there's something really unnatural about it. All those grains are pretty much the same size. That's not something you typically see when you go into your backyard and pick up some dirt. You might get some pebbles, you might get some dust, all sorts of stuff in there. But dunes are very pristine, very pure, very well sorted is what we like to say in geology. And the reason for this is because the size particle that's most easily moved by the wind, and this is the case not just on Earth, but on all the alien worlds in the solar system, is in the range of sand. So basically what's happening is the wind is preferentially moving those sand-sized grains downwind. The smaller grains, there are a number of reasons why smaller grains are harder to move. I think the most important one is probably that they pick up charge easily and they stick to things. So it's hard to blow them off of surfaces. The larger grains are simply too heavy. And so they get left behind. The larger grains get left behind. The smaller ones, if they do get kicked up, they get kicked off into the atmosphere and they get carried away by the wind because they're so light. So grains move in 4 different kinds of movements. The main one is saltation, and this is what produces dunes. This is what, if you're walking along a beach and the wind blows really hard and your ankles start to sting, that's what you're feeling. You're feeling saltation. Grains are getting picked up by the wind in these trajectories, and they get carried downwind, and here's the end of a couple saltation trajectories. When they hit the ground, a couple things happen. One thing is they might kick another grain off into a saltation event. Another is that there might be a splash of particles that don't go very far. That's called reptation. Larger grains might get rolled along the ground by the impact of these saltating grains, or they might kind of jet forward in something that we call traction. And then what isn't shown on this plot is that the very small grains might get kicked off into suspension. So dunes are built by a process of saltation. So how do sand dunes form? So let's work our way back up from sand to dunes and then to sand seas. The problem with understanding how dunes form is that we don't really have many opportunities to observe dunes forming. Most dunes in the deserts on the Earth are very big, they're very old, they were probably built thousands, maybe tens of thousands of years ago, and we don't really get to see those things in the process of being formed. Not anymore. But there are a few places, and there's only a couple papers. This is the best one that I know of, where people have gone out to places where small dunes form every year, and they've watched to see what happens. How does it happen? So basically, you have a very small patch of sand that forms on a rough surface where the wind, because of the surface roughness, has to drop its load, and sand starts to pile up. And a lot of times, those sand patches will get completely obliterated. They'll be destroyed. But maybe it'll stick around. Maybe it'll gain more sand. Maybe the wind won't be mean to it and destroy it. As it starts to build up, what happens is that the wind flow over that sand patch starts to change. And eventually, on the far side, the wind drops enough that as the dune builds up, it can start to avalanche on the far side. It can oversteep and start to avalanche. And eventually, the dune becomes large enough that not only do you have avalanching, but right at the brink of that dune, right where the avalanche starts, you have separation of flow. So that's when you start to get into what a real dune is like, a self-sustaining dune. And eventually, the dunes kind of merge together, and they start to become more regular in shape and in size. And eventually, if it keeps going, if nothing comes along, if there aren't winter storms that come and wreck the whole thing like it does in this particular site, then you'll have a nice self-sustaining dune field. So I've been talking about dunes for a while now, but what are they good for? Who cares? Okay, they're pretty, but so what? Well, the really interesting thing to me about dunes is that they're interesting they add a component of understanding climate change in the past that I don't think many other features can give us. And here's a really nice example on the Earth of one of those things. This is from a study that was done about 10 years ago in Mauritania off the west coast of Africa. So here's a dune field, and this is the Atlantic Ocean. The thing to notice here are these three big bands of dunes. Each of these is a very large dune that formed a very long time ago. We know that because these guys took a sample of sand and dated it from the cores of those dunes to about 25 to 15,000 years ago. And that corresponds to the height of the last glacial episode on the Earth, the last glacial maximum. Now, if you zoom in and look more closely at these dunes, look at this area here, which is in the middle panel, you can see that there are some smaller dunes. Basically, what's happened is those big old dunes were built, and then they became stabilized, and then later on, something happened, and those dunes started getting reworked into smaller dunes. And those dunes, that sand dates to 10 to 13,000 years ago, which corresponds incidentally to the Younger Dryas, which was a cool period that we encountered on our way out of the last glacial period. So basically, the big dune building episodes in Africa seem to correspond to cool and dry times. If you zoom in yet again, it turns out that there's a third set of dunes. And the sand in these dunes dates to about 5,000 years ago. So yet again, these secondary dunes are being reworked into tertiary dunes. So we're seeing three different events of dune building here. Successively smaller, successively less impressive, but we can date them and we can correlate them to climate changes that we are aware of already. And the interesting thing about them, and maybe what they give us that we didn't know before, is something about the wind patterns. Because if you look carefully, you'll see that the dune orientations shift. These, the big old ones, are northeast-southwest oriented. The secondary ones are a little bit more north-northwest, south-south, north-northeast, south-southwest. And then the smaller ones, the more recent ones that are active today, are almost north-south. So there's been a shift in the wind regime. And that tells us something I don't think we really knew before. So what I'm trying to do is apply these same concepts to the solar system. What can we learn about dunes on Mars or Titan? What can we learn about climate change on Mars or Titan that we wouldn't have gotten from any other source? So on to the solar system. Okay, before I jump into what we see on the solar system, I really want to bring home to you just how different the alien worlds are from one another, because they differ in very, very fundamental and dramatic ways. For one thing, the gravity changes by nearly an order of magnitude. Titan is very, very small. Its gravity is not very strong at all. Mars is a little bit in between, and then Venus and Earth are fairly similar to one another. The air pressure, remember it's air that moves sand, varies by 4 orders of magnitude between Venus, which is nearly 100 times as thick as our atmosphere, to Mars, which has an atmosphere that's maybe a little bit less than 1% as thick as ours. And then Titan, strangely, is a little bit more like ours than the others. The air temperature at the surface, the mean air temperature, also varies by quite a lot. Venus is hot enough that lead is soft. Mars, a really hot day on Mars is still a very, very cold day in Antarctica on Earth. And then Titan it's a moon of Saturn. It's way out there in the solar system, so it's extremely cold. So we're seeing a wide range of many different basic properties. Also note that the atmospheric composition varies by quite a bit. So where are the dunes on all these worlds? So these are maps of each of the worlds. Venus, Earth, and Mars, I've shown you topography. Titan, we don't really have a good topographic map yet, so I couldn't show that. So instead, I've just got an image mosaic of Titan. But the white areas, these are places where we see dune fields and sand seas on all these worlds. The thing to really get from this, I'm going to zoom in on each of these, so don't squint too much. The thing to get from this is that the coverage varies quite a lot from one world to another. So down here in this table, I've got the coverage in millions of square kilometers on each of these worlds. And then I have it as the percent surface area, where I've included the ocean terrain on the Earth, so we're looking at the entire planet. So, for example, on Earth, about 1% of the surface of Earth is covered by sand. Mars, it's 0.6%, which is not too different, but a little bit less. But look at Venus. We don't see a lot of dunes on Venus. Why not? Well, I'll talk about that in a minute. And then Titan, look at that. 20% of the surface of Titan is thought to be covered by dunes. That's really amazing. This is why I love planetary science, because you get the strangest things. So let's start with Earth, which we're most familiar with. Here's a map of Earth. And this time I've divided the sand seas up into whether they're active today, whether they're partially active, or whether they're stabilized in the present climate. And you can see most of them are in the Sahara, where you'd expect them to be, in the Arabian Peninsula, in Australia. Here's the Kalahari, here's Central Asia. And there's some in the western United States, and there's some in South America as well. The reason that they're located where they are has more to do with climate than anything else. So here's the total rainfall across the globe on all the continents. And you notice that the sand seas have accumulated in places that are very, very dry. Where it doesn't correlate very well with dry places, note that these are sand seas that are stabilized now. So that gives you some hint that maybe they were built up in a time where the climate was just very different from what it is now. So let's move on to Venus. Venus has 2 known dune fields. They're not very big. There's one here, and there's a teeny tiny little one here that's so small I had to draw an arrow so that you could see it. Here's a picture of the bigger one, or part of the bigger one, and I think this is the more convincing of the two, honestly. So what you're seeing, these tiny little ripples, the dark white that you're seeing here, those are the dunes. And they're not as small as they look. They're actually several hundred meters across. So they're not tiny. And also notice these wind streaks here too, which really tells you that, okay, the wind is blowing. And these things are transverse to the wind, so they're probably what we call transverse dunes. But where are the rest of the dunes? We see thousands of wind streaks on Venus, just like these, all over the place. Where are the dunes? Well, there's one suggestion that maybe there just isn't a lot of sediment on Venus. It's plausible. On Earth, most of the sand that we see is created by rivers, by beaches, by water action, basically. Venus doesn't have any oceans. It doesn't have any water. It never really did. So the supply of sand is probably very low on Venus. But I do want to caution that the only information we really have about the surface of Venus comes from the Magellan radar, which 20 years ago was state of the art, but these days we think we could do a little bit better. We could do more than just barely resolve these things. We could probably map out much smaller dunes than these hundreds of meter size ones, which are barely resolved in these images. So there could be 50 meter size dunes, 10 meter size dunes, 100 meter size dunes that we just can't resolve. Another point is that with radar, it's very dependent on look direction. And that's a problem when you're looking at linear features, because if the linear features are oriented the wrong way, they'll be invisible to the radar. So it's entirely possible that there are dunes that could have been resolved by the radar that it just couldn't see. And until we have more information, which as a good scientist, I always want more data, Until we have more, we can't really say much more. So that's all I'm going to say about Venus. So on to Mars, my favorite. Mars is a place of extremes. And when it comes to sand seas and dune fields, it's no exception. It's very much the case on Mars as well. If you look, you see one enormous sand sea at very high northern latitudes. And then over the rest of the planet, there's a lot of tiny little dune fields that are scattered all over the place, although there seems to be a concentration at high southern latitudes. I'll talk about these later. This is the focus of the study that I'll be talking about. But I'm going to zoom in on that northern polar sand sea. So this bright stuff that you see is the northern polar cap. All of that is water ice. And here's the North Pole right here. I'm going to zoom in on this area. All of this dark stuff, those are all dark dunes, all of it. So here's that area. Here's the polar cap here. And I love this image. It's so dramatic. Here is an actively eroding scarp, just cut right into the polar cap. And off of that is shedding some dark material, dark sand, that is building up into dunes that are being transported along this corridor and being added to the sand sea over here, which is just enormous. So I'm going to zoom in on this area here just to show you. If you didn't believe me, yes, they really are made of dunes. Notice that they're dark. Most of the dunes on Mars are dark. Most of the dunes on Earth are bright. On Earth, they're made out of quartz, feldspar, crustal rocks, basically mostly granite that's been eroded away. On Mars, the rocks on the surface are made of more mafic materials, things like basalt. And so that's what the dunes on Mars are made out of, for the most part. Although I will point out that this northern polar sand sea, people have detected with infrared data the presence of gypsum. Remember the New Mexico sand dune image I showed you with the gypsum in it? Some of that stuff is here too, and we don't really have a good idea why it's in the dunes. All I can tell you is that it is really sand. It really is in the dunes. It's not in the intervening areas, and we don't really know why it's there. So here's a comparison of sand sea sizes on Mars and Earth. The plots really aren't exactly the same thing. They look similar, but they're not, so I want to go through this slowly. Here we have the size of dune fields versus their number. And there are two different things plotted here. The dots are the number of dune fields, and then the bars show the area of the dune fields. So on Earth, let's see, just if you can't read the numbers, here's 1,000 square kilometers, and here's 1,000,000 square kilometers. So by number, there aren't very many dune fields or sand seas on Earth that are 1,000,000 square kilometers, but there are a lot that are much smaller than that. However, the bulk of the area covered by those sand seas are in the big ones, those greater than 30,000 square kilometers. Do you remember that number? That's right here. So you can see why they picked that number to define sand seas versus dune fields. So we tried, myself and some colleagues, to reproduce that plot for Mars. And it turns out it's a lot more hard than you might think. This chart, just for reference, ends at 8,000 square kilometers, which is here in this plot. So it starts here. The biggest dune fields that we see on Mars are here. And you can see that the bulk of them are around 500 square kilometers. They're not very big compared to the ones that we see on Earth. And again, there are more small ones than big ones. The roll-off here that we see is probably has to do with the technique we use to study the dunes. We weren't looking with the highest resolution images. That would just take forever to find them all. But there are probably more small ones that, give me a couple grad students and I can go fill out this chart. The one thing that isn't included on this is the northern polar sand sea. That one would be off this chart. In fact, that one fits nicely into the Earth chart right about here. It's 750,000 square kilometers, which, by the way, covers 80% of the dune coverage area on Mars. So the vast majority of the sand on Mars is in that northern polar sand sea. What does that mean? Okay, well, Mars has a lot of small topographic traps like craters, and it could very well be that where the sand forms, it just happens to be where there's a lot of those topographic lows, and that's where the sand happens to pile up. On Earth, most of the big sand seas are in very stable, tectonically stable basins that have been that way for thousands of years and aren't really doing very much. And so the sand can just pile up, kind of like it's done in the northern lowlands on Mars into that one big sand sea. But so topography, it could just be, a boundary condition, basically, that defines why things are different on Mars. But there are other things that vary as well. We think the sand supply, for example, is lower on Mars than on Earth. Terrestrial sand, as I've said before, comes from erosion of crustal rocks, mostly by water action. So you stand in a dry riverbed, you see a lot of sand. You go to a beach where there's a lot of wave action, you'll see a lot of sand. On Mars, there's not a lot of water action these days. There was once in the past, and that could have produced a lot of the sand that we see, but we don't know how much. There's also impact cratering, volcanism, glacial scour. These are other processes that can and do produce sand on Earth, but may be with the dominant process on Mars. However, with the current absence of abundant water on Mars, we think that production rates on Mars are significantly lower. There's also sand availability, which, when I say that, what I mean, this was the slide that I skipped. What I mean is sand that is available for transport. So it's sitting on the surface and it's just waiting for a gust of wind to come along. So it doesn't have any vegetation, keeping it from being eroded. It's not buried. It's not covered by water. On Mars, there's not a whole lot stopping the sand from being moved. It's just sitting there if it's on the surface. Earth, 70% of it is covered by oceans. Once sand goes into the ocean, it's not coming out. So there's no global scale sink for sediment on Mars. That stuff was made, and it gets, 4 billion years ago. It's probably been transported around on Mars on and off for billions of years, whereas on Earth, sand gets created and destroyed over and over again. Then there's sand transportability. The Martian atmosphere is much thinner than the Earth's atmosphere. It has been for a very long time. And so it takes a lot more energy to move sand on Mars than it does on the Earth. So these two factors could define why we don't see as much sand on Mars as we do on Earth. So on to Titan. So the plot I showed you before, all of this stuff was white. But I just wanted you to know that we haven't seen dunes in all of those places yet. The areas that are white here are places that the radar and Cassini has actually imaged, and we know that those are covered in dunes. Those have really been mapped as dunes. The brown and blue areas have not yet been mapped by the radar, and they're areas that correlate very well with where we expect to see dunes based on the radar swaths. So when the radar does cover those areas, we'll be able to fill them in, and yeah, it's probably covered in sand. So if they're right, if the people who calculated this are right, then yeah, the surface area on Mars, on Titan that's covered by sand, it's 20%. It's huge. It's more than 3 times the coverage on the entire planet Earth. And Titan is very small, remember. Oh, the other thing I wanted to point out is, notice how they cluster around the equator on Titan. That's something we don't see on Earth. It's not what we see on Mars. It's very different, something else completely all over again. So most of Titan's dunes are linear dunes. That means that the sand on them is transported basically parallel to the shape of the dune. So we see dunes a lot like that on the Earth. Here's a case in Namibia where the dunes are very similar, both in size and in morphology. You can see how they get diverted around obstacles on the Earth. And here's Titan. You can see it getting diverted around obstacles. So they're thought to be probably the same kind of dune that we see in those deserts on Earth. The problem with this is that based on the diversion around obstacles on Titan, the movement of sand goes from west to east. And remember how I showed you that all those dunes were near the equator on Titan? Well, on Titan, just like you get on Earth, there are trade winds that should blow from east to west. But the dunes are saying the sand is going from west to east, so what's going on? This is another mystery. This is something we really don't have a good answer for yet. There's a recent paper from last year where somebody had a very good look at an atmospheric model and thinks that maybe he can explain what we're seeing. But I think really we need to refine the models more. We need to understand more of what's going on before I really want to explain to you what this guy's idea is, because it might be right, but we just don't know enough to say yet. So what does that mean for Titan? Well, the first thing I want to say, which I haven't really said yet, is that sand it's dark not only in radar, but in the infrared data as well. And that's consistent with hydrocarbons. Remember how cold Titan is. It's a very, very cold place. And the atmosphere has a lot of hydrocarbons in it that can condense out and basically rain out on the surface. And so that's thought to be the source of most of the sand, which is kind of crazy. I mean, you can imagine sand raining out of the atmosphere on Earth. It's just insane. So here's a cute little factoid. If that's the case, then those dunes on Titan are the largest sink of carbon, which is about 1,000 times the coal carbon on all of Earth. So anybody who wants to do some mining, go. Yeah, it's cold.
Windmills work there too.
Well, we hope so. We don't really understand why all the dunes are at the equator. One thought is that the models suggest that winds are simply too weak at high latitudes, so maybe if there is sand at high latitudes, it just can't pile up into dunes. But it also may relate to sediment source and sediment availability. Maybe if that stuff is raining out from the atmosphere, it only does so at the equator. We really don't know. There's just too much we don't know yet. There's one thing we can say, though. All those dunes, pretty much across the planet, are more or less all the same size. That means that they were probably all built over the same time period, so that it's all one extended sand sea, effectively. So that's consistent with the idea that the source is raining out from the atmosphere. So there's no particular spot where the sand is eroding from. It all happens everywhere, and it's all happened at once. Again, something very strange relative to anywhere else in the solar system. So now I'm going to move on and talk about work that I've done with a colleague of mine on Mars. So remember that plot where I showed you Mars with the big northern polar sand sea, and then in the southern hemisphere there were a lot of tiny little dune fields. Those dune fields are what we mapped, and there are a lot of them. Our study area started at 50 degrees south and extended to 90 degrees south. So here's the South Pole, and here's the South Polar Cap. And all of these little yellow dots are dune fields. There are almost 1,200 of them. Mapping took a long time. They cover 116,000 square kilometers, which sounds like a lot, but really it's only about 1/8 of the coverage of sand that we have on Mars. Remember, 80% of it is locked up in those northern polar sand seas. Most of these dune fields are small, less than 100 square kilometers in size. So what we were looking for was evidence of climate change. We know that there are a number of other features on Mars that show some evidence of climate change, and I'm not going to list them out for you all here. Some have been identified, some have simply been modeled, some are morphology on the surface. I think the most famous one is terrain softening. This came out in the mid-'80s. It was a Squires and Carr paper, it's this one, where using Viking data, they looked at low latitude craters, like around, I think this one is minus 14 degrees latitude. And you can see that the rim is nice and crisp. Even though it's a fairly degraded crater, you can still see the rim. It's still very much there. And you compare that to a typical mid-latitude crater, and the rim is much softer. Their idea was, and still is supported by a lot of other data, that there's ice in the ground here, or there was at some point. And that ice became fluid and flowed just enough that it could erode away those sharp peaks. So all of these morphological features and data, everything points to the idea that there is ice in the ground at mid or high latitudes on Mars, and that ice can move around with climate. We were wondering if dunes might tell us something. Would it be different? Would it be nothing at all? What would it be? So we did find something, and I'm not going to show you all 1,200 dune fields. What I'm going to show you are the 6 different morphological classifications that we came up with. I'm going to start with dunes that look like they might actually be active today and work my way progressively towards more inactive looking and degraded looking dunes. So here's the Russell Crater class of dune fields. These dune fields look a lot like terrestrial dune fields, except that they're dark. They look like they might be active today. They have nice, crisp brinks, and they have slip faces that we can identify and morphological shapes that we're familiar with. When I plot up a histogram of where we find these things, here's our study area going from 50 degrees south down to 90. We didn't find any dunes poleward of about 82 degrees, so I just cut off the plot here. We find most of those sharp, active-looking dune fields are at the northern end, the more equatorward part of our study area. And the different colors here, the white are the identifications that we trusted the most. So look at the white if you really want to know what we think. So here's the next class. I'm going to run through these quickly. We start to see features that have what we call aprons. It's very thin, just shells surrounding the dunes. Here we see a dune field that has one of those on their southern edge, but nothing on the northern edge. I've never seen anything like this on Earth. I don't know what causes it. I don't have a good idea, but I've interpreted it to be some kind of degradation, something that wasn't there when the dune field first formed and has since come along and doesn't have much to do with aeolian processes. So when we plot up where we see those dune fields, they're not so far north. They're a little bit farther south. They're clustered at about 60 degrees south, maybe 61, 62 degrees south. There's a cluster at higher latitudes that I wish I had time to talk about because that's very interesting too. So here's the next class. These have very well-developed aprons that surround the entire dune field, and the dunes start to look softer, more eroded. So again, we're seeing a sequence of degradation here. And when we plot up where we see these dune fields, they're right smack in the center latitudes of our study area. Moving on to even more degraded dune fields, we still see aprons. We still see dunes that we can recognize as dunes. Wait, you just wait till I show you the next ones. But we start to see a layer of material that has been exposed at the edge of the dune field, almost as if the dunes were formed and then they started to erode away, as if maybe when the dunes were there on the surface, they armored it and protected it from erosion. But now the dunes are being eroded away, and suddenly we see exposed this bright layer of stuff that is also starting to get eroded away. These things are clustered at about 70 degrees south. Moving on, if I showed you this without having showed you the previous images, I know I probably would not have been able to identify this as a dune field, but because we see the sequence, we can say, yeah, this was probably a dune field once, and something has happened to it. These don't really look like identifiable dunes. But again, we can still see an apron, we can see an exposed layer underneath. It looks like there might be bright material that settled out on top of the dunes, which again would be something that's inconsistent with dune activity. And again, when we plot these up, we see that they correspond to fairly high latitudes in our study area. So what I think is going on is that the dunes are simply becoming dissected over time. So here's an example of the Nebraska sandhills in the United States. These are dunes that formed after the last glacial period. And they've got vegetation growing on them now. They get rained on, they get snowed on. They've got gullies coming off them, and they have this really bumpy, rugged appearance to them. I think that's what's happened at high latitudes on Mars. Except, of course, the processes are different. There's frost, there's dust devils, there's cementation. It's not getting rained on Mars. And then finally, the last class of dune fields don't have dunes on them at all. In fact, I wouldn't have known what to do with these if I hadn't seen the other dune fields. You can see that there's layers, you can see that there's an apron, but there's no dunes at all. So the question is, did these ever build up into dune fields at all? Or were they dune fields that have since completely eroded away? Are they just gone? We have no idea. These things are clustered at the highest latitudes. And just to be fair, there were a lot of dune fields that either were not imaged or had bad images, or just the dunes were so weird we didn't know how to classify them. And just to show you, there were a number of them, and they seem to be fairly consistent with latitudes, so I don't think this distribution would mess with any of the distributions I've showed you previously. So here's what they all look like when you put them on a plot, on a map. So here's the South Pole, here's the polar cap, and here's a progression from red to orange to yellow to green to blue, and going from the more active-looking dunes down to the more inactive-looking dune fields. And you notice that the red ones are all at the higher latitudes. And then at about 60 degrees south, this is what I really want you to see in this plot, because I know it's kind of messy and it's kind of hard to see. The dunes are small. At about 60 degrees south, which is this ring right here, things change from red to all the other colors. That's the dividing line between dunes that look like they might be active today and those that show some kind of degradation. And it happens to correspond, incidentally, with the edge of the known ground ice. So basically, poleward of 60 degrees south, the ice is saturated, or the ground is saturated with water ice. So what we think is going on is the dunes are stabilized by ground ice. So that causes the dunes to become inactive. Ice fills the pores between the sand, and the wind can no longer blow them anymore. What's interesting is that the present-day dune field inactivity corresponds with the present-day ground ice. So the dunes are reflecting the present-day climate. So just to add a little bit of support to that, I didn't see any craters in this entire study, and I looked at a lot of images. I had a student last summer look at high-rise images, which can get down to, a quarter of a meter in resolution, so that you could identify maybe 2-meter-sized craters. She couldn't find any in any of the images she found. So she estimates that the surface of those dunes is on the order of 100 years old. Now, that doesn't mean that the dunes were built 100 years ago. That's very unlikely. They're very large. They probably took thousands of years to build up. But something is changing the surface on a time scale of about 100 years, which is odd because they look inactive. They look like nothing's going on. So whatever's happening to the surface of those dunes, it isn't alien processes. It's some other kind of erosional processes that wipes out any craters that we see. So if the dune fields are unlikely to accumulate under present-day conditions, that means they're availability limited. It's not a sand supply issue. It's not a wind strength issue. It's that the sand can't be transported by the wind. And those dunes probably formed in a warmer climate and have since been filled up with ice. And what we think is that as the ice comes and goes, probably as orbital parameters on Mars, things like obliquity change, then the ice comes and goes. When the ice goes away, those dunes might activate, and they might erase all those erosional features. They might erase any craters that might be lingering on them. And then as the ice comes back, they stabilize again, and maybe erosional processes start to act on them, and they start to look degraded again. So those dunes could have been sitting around for billions of years, or maybe millions of years. We really have no idea. So to conclude with it all, sand seas and dune fields are prevalent in the solar system. There are 4 worlds that we know of so far. Their morphology has a lot to tell us. There's a lot of information in those dunes. And sometimes we don't have any other information that we can use to learn about the climate. On Earth, there's a lot of tools. You can go out in the desert and pick up that sand. You can go out and put a meteorology station down and learn about these things. But on Mars and Titan and all these places, we've got what we've got, so we work with it as best we can. And finally, thank goodness, there's so much we still don't know, so I'm never going to be out of a job. And there's always going to be more work to do. So thank you.
Thanks, Laurie. First question, if you had to fit the North Polar dunes into your South Polar categories, where would they fit? Just off the top of your head.
I would say they look active.
And which class does that correspond to?
The red
most?
ones.
Okay.
Although they do have some degradation features, but they're different. So they would fit in with these red guys.
The Russell crater ones.
Yeah,
Simple question on the Titan equatorial drifts, dunes as you call them. Do they perhaps correspond more toward polar drift of things like snowfields as opposed to classic sand dunes or sand seas?
No, they actually have a morphology that is very much like dunes we're very familiar with. So yeah, they really do seem to be dunes. Unfortunately, they're not that well resolved. So it's still a guess, but everything we see, it looks a lot like linear dunes that we see in the deserts on Earth.
Okay, it's not like
No.
I find this feature near the South Pole very striking. The features that are almost circularly centered on the South Pole.
swirlies?
And also, of course, there's the famous North Pole spiral structure
Yes.
that's also centered on the North Pole. Any ideas on what causes those and why they're so centered on the poles?
Yeah, the North Polar ones, there's been a lot of debate over the last 30 years since we found them, 30, 40 years now, about exactly what causes them, whether it's wind or whether it's preferential sublimation, all sorts of things that could cause them. And I'm trying to remember, there was a paper that came out a year or two ago, I think it was a grad student who might have solved it. He was looking at radar data that has penetrated the layers of the ice. And it turns out when you look at the spiral, like a single trough, it actually, you can see it extending through the ice. And so it's a feature that forms, these troughs migrate slowly over time. In fact, that grad student, I think he's a grad student, calls them bed forms. So what we're seeing in the South Pole is probably something similar to what we see in the North Pole, but it's not as well developed. Perhaps simply more eroded.
And another question on your classification. Did you try any automated classification schemes that people are playing with these days?
No, that.
Yeah, I was wondering the difference in gravity and the difference in atmospheric density. I wonder if the sand size of the dunes, the sand size of the grains that compose the dunes would be different on the different.
You know, that idea has been tossed around a lot.
Yeah.
We don't know for sure on Titan and Venus, but on Mars, the MER rovers have looked at the sand that's in. They've actually driven up to some of the ripples on some of the sandy features, and they're very similar to what we see on Earth. It was kind of surprising. But I'm going to take you back to this plot early on. It seems surprising, but when you think about it, it's actually not. Because again, look at these curves. The most easily transported sand size, or the most easily transported grain size on Mars isn't that much different from what we see on Earth. So if you didn't know any better, if you didn't have any data, you might say that if there are dunes and ripples on Mars, we would expect the grain size to be very similar.
Why would the North Polar dunes look active if groundwater or ground ice inactivates them? And I guess I'm making an assertion that there's comparable amounts of ground ice at high northern latitudes as at high southern latitudes. Why would that be?
That's a really good question. The northern polar sand sea is probably an awful lot younger than the dune fields we see in the southern hemisphere. So it might simply be an age thing. Another idea is that the surface is a lot smoother up there. So you have a lot of fetch for winds to come along and blow that sand. They're right next to the polar cap, and you can get really strong katabatic flows coming off the cap. So it could simply be that the winds are just so strong that even if there is ice in them, it overwhelms any cementation process that's going on. And we do see some degradation features up there, but nothing as dramatic as we see in the south. So it's just amazing how different they are.
I had a follow-up question about the two questions about polar. I guess they're referring to the pole of the planetoid. The polar oil-soluble molecules on Titan have different adhesion, and I was wondering what we know about the Titan sand particle size distribution, and with that 5% methane, what kind of adhesion properties those particles might have that are different than the other dunes.
We don't know anything. We don't know anything about the grain size. We have no instruments to give us that information, unfortunately, right now. The only reason that we know that there are dunes, the only reason that we agree that they are dunes, let me put it as scientifically accurate as I possibly can. The only reason that there is general consensus that they are dunes is because they're so morphologically similar to similar dunes that we see on Earth. And that's really all I can say.
Okay, last question.
With the Mars Science Lander mission coming up, I know they've narrowed down the landing sites to just a couple now.
Yeah, there's 4 right now.
Dunes fall into any of those?
Yes. One of them, if we go to Gale Crater, the rover will go straight by some dunes, and I am so excited. I really hope we go to Gale Crater. But all of the other sites have their own interesting things as well. There's ripples at each of the sites. I'd be happy no matter what, but most of all, Gale Crater.
When do you find out?
What would we find out?
Yeah, no, when do you find out which of the 4?
Sometime this spring. I don't know when they're going to decide. Does anybody know?
Well, it'll be en route that we find it.
Yeah. Yeah.
They won't actually decide between the last 2 until they're en route, I'm sure.
Right, and somebody at headquarters will make the final decision in the end.
Yes, his name is E. Weiler, and he's the head of NASA SMD. Laurie, we have a special memento, which I've opened for you there. That's a special SETI mug.
Awesome.
So if you all join me in thanking Laurie for a great talk.